It's a pleasure to introduce today's speaker, Samuli Siltanen from University of Helsinki. Samuli received his PhD in 1999 from TKK, nowadays Aalto University. And after his PhD, he worked in the industry as an R&D scientist in X-ray imaging companies. And in fact, if you've been to a dentist for a dental implant X-ray, there is a chance that there has been Samuli's algorithms running in the X-ray device. Since 2009, he has been the professor of industrial mathematics at the University of Helsinki, and he's also currently the vice dean of Faculty of Science. Samuli works on inverse problems in medical imaging with the goal of developing efficient numerical methods that have a solid mathematical foundation and can be used to solve real-world problems. He has won several awards, including the Mathematics Prize of the Finnish Mathematical Society in the previous slide. And of course, Samuli is also a highly visible communicator of mathematics and science to general audiences. He's doing this through his YouTube channels, his popular science book, Step into the World of Mathematics, which is available both in Finnish and English, and through his regular appearances in media, such as the TV shows Ylen Aamu-TV and Puoli Seitsemän. Today, Samuli will talk about the magic of math, 3D X-ray vision. And let me mention at this point that the talk will be recorded and put on the YouTube channel of the Mathematical Society. In the end of the talk, it will be possible to ask questions, and the questions will not be recorded. But Samu, please, the floor is yours.
Thank you so much. And let me start by thanking for this opportunity. It's really nice to speak in the Finnish Mathematical Society colloquium. I've been a member for a long time. I think it's a super important community for Finnish math, and one of the oldest societies in the world. Okay, so my topic today is X-ray imaging, and especially its three-dimensional version, tomographic imaging. I'll quickly mention, like Mikko said, actually, I have this YouTube channel. Also, I have a new one called Professor Sam, which is more, it's in English and also educational. And yeah, Mikko also mentioned the popular book. So it is my passion to try to tell about mathematics to everyone possible. This talk today actually had a test run in New York City a year ago in the Museum of Mathematics talk series, Math Encounters. I believe I was the first Finnish speaker in that series, which was quite an honor. So X-ray images, they are the base of the tomographic imaging. And let's take a quick look at the history. So this is Wilhelm Conrad Röntgen, who invented X-ray images and actually got even a Nobel Prize for it. It's curious to know that about the same time, there was also this guy, Nikola Tesla, having his electricity show. He traveled with this electricity show and presented big indoor lightnings like this. And he had actually noticed that sometimes when the lightning is on, he can see the paint glow in the walls. And when he put his head next to the wall, he could see inside his head in the glowing paint. We know now more about radiation, and this is not recommended anymore, but I'm sure he had a good time. This is a picture from my lab here at University of Helsinki. There's Zenit Purisha, who actually defended her thesis some time ago and is now back in Indonesia, working at the University of Gadjah Mada there, and Alexander Meany, who is just finalizing his thesis. Alexander actually built this little X-ray lab. We can do lots of experiments. For example, we can put a rose inside the cabinet. On the left, you see X-ray source. When we put the electricity on, there are X-rays. We don't see them actually. I just put here some graphics. I mean, the human eye is not sensitive to X-rays, but the camera is. So we have this Japanese Hamamatsu camera that will detect X-rays and give an image like this. So here we see that whatever is black has collected all the photons coming in from the X-ray source. So there's nothing between the source and the camera pixel. And then the lighter shades mean that there has been some material on the way of the X-ray. So this is also kind of a measurement, how much stuff the X-ray encountered. And this actually brings us to mathematical line integrals. Oh, hey, since Mikko already also mentioned these social media activities, I have to also mention that we had the hydraulic press channel visiting Kumpula. We did some exquisite X-ray experiments, not so scientific maybe, but entertaining. So here's an old digital camera gradually pressed with the hydraulic press under X-ray camera. So if you ever wondered what is the life of a professor of mathematics, it consists of imaging experiments like this. So actually, how to connect mathematics with these X-ray images? When we see an image like this, this poor patient has a broken nose. This is, of course, one of the strengths of X-ray imaging. We can see bones very clearly. But now, if we zoom in this image, let me pick smaller and smaller pieces of this image, and we start to see pixels, and the grayscale value inside the pixel is shown as a number in the computer. So this is the connection to mathematics, because of course, as we know in this audience, numbers are central in mathematics. So then let's go to slice imaging. And I mean, images like this. We cannot take such a slice image by just putting the patient between the X-ray source and the camera. Making such a slice image actually requires some mathematics. How is it done? Well, before going into that, I had a wonderful question from a school kid in one of my school visits asking, why is there bone inside the brain of this person? So these white parts. I was caught by surprise. My knowledge of anatomy was not nearly enough. So I studied this situation and realized that actually the red line here shows how this slice is positioned in the 3D structure of the head. So inside here, there is some bone that's visible here. So it's just, the human body is rather complicated. And well, yeah, if you're not a medical professional, it's hard to appreciate sometimes. So how to take these images? It needs a machine, something like this, like a big donut. Inside the donut, what's going on? It's actually pretty impressive. There is an X-ray source and camera combination inside the donut, rotating very fast. It can even go like a couple of rounds per second, and it weighs closer to a ton. So it's really engineering-wise, it's difficult to make these machines. Let's take a look at the very first machine like this, built by Hounsfield in the late 60s, early 70s. This is meant for imaging the head, and why I picked this old one is that the imaging geometry is very nice for the mathematical explanation. Namely, first of all, we think of keeping all the X-rays traveling the same direction, moving the source like this, and collecting a profile, line integral of stuff along each of those X-rays. We can see actually in the machine that the yellow arrow shows this degree of freedom in the machine, linear movement. But there's another one. It also can rotate. So we can collect this linear profile and then turn the machine. And then doing this many times in this old machine was quite slow. But anyway, we could collect this kind of profile from or along many directions of projection. So those yellow profiles are our information of the patient. And now the inverse problem is, The machine gives us yellow profiles. The inverse question is, what is in there that gives exactly these profiles? One of the very basic questions in the field of inverse problems. How to recover a function of two variables if we know the values of its line integrals along any line. Then one of the things today is I will explain a process called filtered back projection, which looks like this. We are, in a way, projecting those measurements back to the image domain and revealing what is inside. So one of my goals today is to explain what is happening in this process. So indeed, this technology was invented by Hounsfield. Also, this problem was studied by Cormack, and they got a Nobel Prize for this in 1979. On the right, you see one of the very first slice images of a human head. And let me note that you can see between the bone and the brain, it seems that there is a black gap here. So they thought, oh, there's some air inside the head between the skull and the brain. We didn't know. And actually, it turns out there is no air between the skull and the brain. This is something called beam hardening. When making these images, we have to take into account the different colors of X-rays or different energy, and we have to make a correction. So mathematically, we are not quite measuring line integrals. That would require monochromatic X-rays, which we don't have in this kind of technology. It can be corrected for, but real life is often more complicated than the simplest mathematical models. How is this method used? Well, this is quite an everyday tool. One of these years, I remember one statistics in the United States, in 1 year, it's like 50 million CT scans in that country. So it's a very, very common tool. One thing to see is what is happening in the brain. Here we can see ischemic stroke. So this dark area is not getting blood. So this part of the brain is in danger. Another possibility is that there is bleeding in the brain. So blood shows up as this white blob here where it's not supposed to be. The problem with this is that the symptoms are the same in both cases. So by just examining the patient outside, the doctor doesn't know if blood thinning medication is appropriate, like for this patient, or is it rest for this patient. Definitely don't give blood thinning medication to this bleeding patient. So they have to make a decision, but as you can see with CT, it's like night and day, ischemic being like night because it's dark, and maybe this one is the day because it's bright. Okay, anyway, this is a very good tool for many, many uses. And now, dear audience, it's time for a little test. Is your brain wired tomography-wise? Can you solve these tomographic problems I'm serving you? Let me first explain how these work. So there is some object here, the white rectangle, and what I'm showing is actually the line integral here, and because this is homogeneous, the yellow profile function is just actually the length that the X-ray travels inside the white shape. So for example, for this ray here, we see we have a big number in the function. It's the length of the ray inside. This part, this ray is going only a very small bit. So when we follow this ray, we see just this very small bit recorded. But of course, I mean, in the little mysteries I give you, I will show you the data, and then the problem is what is inside. Are you ready for the tests? I don't think anyone can ever be ready for this. So let's just go. All right, here it's actually 3 targets, and I'm showing the data of all of them, but in the wrong order. So I'm ruling out actually the possibility that they will be in the same order. They are not. So I scrambled them. So which is which? Immediately we arrive to some feature of inverse problems called non-uniqueness. for example, here, we see that measurements 2 and 3, the profiles are exactly the same. So we cannot make the difference between 2 and 3 measurements in this direction. But actually, measurement 1 already reveals what I suspect maybe some of you already know, which one is measurement 1 and the shape. And then actually, we can look at the horizontal rays. So we already knew measurement 1, it corresponds to the third shape. So we don't need to look at that anymore. And now the question is only measurements 2 and 3, which one is which here? This was level 1. We'll go to level 2. This is again written characters, but reflecting a little bit maybe my postdoc time in Japan, I picked kanji or Chinese characters. So we have here river, tree, and rice field as the options. Let me again a little bit stop these measurements and see that according to my devious plan, 1 and 3 look a bit same, not completely the same, but anyway similar. Number 2 is different. If you want to guess, just go ahead. It's hard maybe to reach the online audience, but anyway, so maybe we can say that number 2 is the river. And once we turn vertical, so number 2 is solved, and now actually we can see that number 3 seems to be character 3. A little pun there. Great. So let's do another one. This is a bit more difficult, maybe. I don't know. I mean, I'm sure this room is pretty much filled with natural tomographers, and online, I'm sure we have some more. Anyone wants to guess or share knowledge? Again, try to help. So, for example, now I think number 3, the measurement number 3 should be kind of obvious because of the corners in the profile. I think only one of these shapes has rectangular. So I think this must be R. Maybe the other 2 we can see there should be quite complete left-right symmetry in the profile for number 8. So I guess maybe it's this number 1, and so on. So we can actually take a look. Here is the solution. Okay, we did already 3 levels of tomographic problems, but there's more. Now we go to more written characters, but not any more homogeneously white. This is modern writing. And now the thing is, which is which? It's more difficult because the profiles are not anymore just lengths of the pathways inside the shapes, because darker gray means less material is accumulated and brighter pixel means more material is generated. I can see part of the audience scratching their head. Not so easy anymore. Maybe number 3 is the easiest because there's some kind of a round shape pretty much staying. So this is actually the smiley. Then it's a bit hard, even if we align the rays same direction than the unicorn's horn, we don't really see in the profile any unicorn horn. It's not so simple. It is because of the grayscale in the images. So even if we align the X-rays with the unicorn horn, it's not such a big effect because it's gray. And now we arrive, after all these level 4 mysteries, we arrive at a medical mystery. So here is some data given to us by a hospital scanner. What is there? We need to help this patient. what is there. So in this case, I'm showing three options. It's either ischemic stroke, A, or hemorrhage in the brain, B, or a rare but serious condition called unicornism plus ischemic stroke, which is C. Any guesses from the audience? At least to me, I can admit this is pretty much impossible, even if I know the result. So it is ischemic stroke, an added complication by the unicorn. And now we arrive at an observation that we don't have three options in the hospital. We need a method that will calculate what's inside, regardless what is there. So let's go to filtered back projection, which is the most classical method for calculating these slice images. And I will explain it like I'm going with this parallel beam geometry, like we have been looking at. Modern scanners actually use either fan beam or cone beam or spiral geometry, but the principle is the same. We know some line integrals. We need to make some formula to make the image. So filtered back projection has two parts, the back projection and the filter. The back projection works like this. We take the profile, the yellow curve, and we throw it back into the image domain by putting a bright pixel along the way of a big value in the profile, the black pixel along some way. If there's a zero value in the profile, we send zeros, and grayscales in between. And then we use several directions. We keep sending back, and we add up the numbers in the images. So now that we keep using this, we see that some kind of image starts to appear a little bit. And here I didn't use all of the measurements. We can actually do a continuous sweep or integration over the angular variable. So the picture builds up, and we can see the back projected slice image, which is nice, but not completely there. Because, for example, we know that outside the patient, there should be nothing. So this should be completely black on the edges, but it's not. So there's some kind of weird blurring going on, and therefore we need the filter. So we actually take the Fourier transform, or in practice, we do the fast Fourier transform, FFT. I'm showing the absolute value of the logarithm of the FFT here. And then we apply some modification on the frequency domain. This is the Calderon operator. I'm multiplying each pixel value by the distance from the center of the image, just to reveal what's going on here. And then when we do the inverse Fourier transform, actually we will get the original target back. This is a beautiful theorem from 1917 by Johann Radon. I know, well, we have Kari Astel and Eero Saksman and others here who know some things about the Fourier transform. So let me still divide the Fourier transform into little pieces to maybe make it a little bit more intuitive. So if I cut away some part of the Fourier transform and calculate the inverse, we see what does those parts of the Fourier transform represent. It's kind of hard to see, but if I zoom in, we see that this here, which is the high frequency part, I only leave the things around the edges. So you see there are some very, very tiny oscillations left here. And this is a rest of the image, which is very, very smooth. Then we can do another, I pick out another piece. So we have here just like an annulus or ring of stuff. And again, if we do a little bit of magnification, we see that in the first one, we have the tiniest waves. In the next one, we have a bit bigger waves. And if I continue this division, we see that we have progressively larger and larger wavy features. And what is nice here, or There are many things nice here. One of them is linearity of the Fourier transform. In the top row, I believe it's rather obvious why, if I sum up the images, I will get the original image back. But the same happens for the bottom row images, which is not as obvious, maybe, at least when we look at them. But that's what happens, and it's super useful. And now we can also change the filter side. On the Fourier domain, the high frequencies will boost a lot. The ring we boost a little bit. The middle one we just keep. Then we reduce the center parts like this. So then all of these images change. And now again, I will sum them up. The top row again is kind of clear why it sums up the same, but then the bottom row gives actually the desired image. The same thing, this operation going to the Fourier side, multiplying by the distance from the center and coming back. When we apply it to a random photograph from the internet, we can see that it will enhance edges and boundaries. So it also works as an artistic tool if one wishes. It is a pseudo-differential operator called the Calderon operator. And here we actually see what happens. Well, this is again, and the modern way of writing it is that we take the radon transform, that's a parallel beam measurement. We apply the adjoint of the radon transform operator, which is the back projection. Then we apply the Calderon operator, which is this frequency domain trick. And in my or the way I calculate, we still need a factor of 1/2. This is the content of a legendary paper by Johann Radon from 1917. He wrote it with a Stieltjes integral like that. It's a bit different notation than we use these days, so mine is written in a bit different way, but it's the very same thing. And at this point, I have a habit of encouraging all us mathematicians that when there is a legendary idea, let's try to communicate it as widely as we ever can. Because in Radon's case, this formula was published in 1917, and then later in the 50s and 60s, Cormack and Hounsfield reinvented the whole tomography thing without knowing Radon's work. Maybe we would have been saving lives even sooner with tomography if the communication would have been more efficient. Okay, for anyone who wants to know more about this stuff, please visit my new YouTube channel, Professor Sam. I'm building up a lecture series of some like 5-6 minutes little pieces, which actually I use also for my university teaching. Oh, hey, there's a comic relief. What happens to Duplo bricks under extreme pressure and X-rays? Maybe this Danish technology will take the pressure. No. The pressure was too much. Yeah. Yeah. Well, just regular day in a professor's life. All right. So I described you the classical way of tomography. It was pretty much, in principle, finalized in the 70s. Of course, there has been a lot of technology development after that with all the spiral geometries and stuff. But somehow the essence, I think, is pretty much the same. And the essence is saying that if you can measure your target or patient from all around and many, many, many angles, then these kind of integral formulas are a good way to go. You will get really good images very fast. Everything is wonderful. And then one can ask, what is there to research for an inverse problems guy of the modern day? And my answer is that there is a lot to research. If we are pressed on time, we have to measure very quickly, or we shouldn't radiate the patient too much. Then we have less images or more noisy images. Sometimes, like in 3D mammography, or examining the weldings of pipelines, we physically cannot measure X-rays from all around. We are limited to a restricted angle. And then the math gets really sticky. I mean, everything is much more ill-posed, much more difficult, so delightful for inverse problems researchers. And for those approaches, usually this filtered back projection is not the best option to go. Let me show you a little example. We measured with Keijo Hämäläinen when he was still in this university. We measured this in his lab some 10 or more years ago, and we put a walnut inside the machine. And now this is a slice through the walnut. We picked walnut because for an amateur medical expert, or not expert at all, it kind of looks like a brain. There's a skull-like boundary, and inside there is a brainy thingy. Please don't reveal me to actual medical doctors about this. But yeah, from the mathematical point of view, it's kind of similar. So we actually took 1,200 projections of this walnut. So we turned it only a very little bit between these images. So we get this super detailed slice. But then if we kind of simulate the situation that maybe we have to save our precious walnut from too much radiation, and we only take 20 images, I mean, all the full angle, but with very big angular steps. Then on the right-hand side, you see the filtered back projection image, which is not as good as the left one. It's maybe not fair to compare them because the other one has much more data. But now the point is that in many practical situations, we have to deal with very restricted data like that. And this is maybe not the best image. Maybe it's not the worst either. But let's see some options. From the very same data, this is done with the Haar wavelet sparsity. This is total variation regularization. This is with Dobbe 2 wavelets, L1 norm sparsity. This is total generalized variation, which produces piecewise smooth reconstructions as opposed to TV giving piecewise constant. This is a shearlet sparsity reconstruction, and this is the filtered back projection. Now, the point here is that these look very different. When I started talking about this stuff and showing these images, I was saying that this one is so much better than this one. But after feedback from audiences, I'm not so sure anymore. Actually, it depends who is looking at the image and what are they looking for. For some person, this may be the most useful one. And for another person, another task, one of the other ones can be the best one. So we actually need a range of methods designed for different purposes. There maybe is not really a general method that would always give the best one. That's the way I think about this these days. So anyway, I try to argue that there's a need for methods that can deal with very missing and lacking data. And then we don't do it anymore with the back projection and filtering. Another way is to divide the unknown area into pixels or voxels in 3D. And then we think that, okay, inside each pixel, we have unknown material, but it's homogeneous. Inside the little square or cube, we assume we have homogeneous material with X-ray attenuation value. And then in this finite dimensional model, we will find the best pixel values. So the measurements become actually very simple. So this is, I think, at least for me, this is the simplest possible example I could come up with. But we will see a surprising difficulty even with this one. So now we have a square patient, two-dimensional, that has some internal structure, but only 4 squares internal. And our first X-ray is going there horizontally, and our X-ray camera, after some calibration needing a logarithm, it will actually calculate the sum of those numbers in the row. We assume that the small pixel has side length 1. Sorry for all the physicists in the audience. This is the math way we just randomly put stuff to be just 1 without any meter or kilogram or something. So anyway, we can, after calibration, think that our camera measures the row sum. Why did I have this here? Oh, sorry. yeah, so we have a patient, and maybe we can think that the numbers 2, which is not so much attenuating X-rays, maybe that's muscle, and the bigger numbers, maybe they're bone. So we kind of have 2 internal organs in our little square patient. So now we have 2 X-rays horizontally. We have the row sums of this little 2x2 matrix. Now we turn our tomography device. Now we have column sums. So this is our very simple tomography situation. This is our direct problem. If we know what's inside, it's very, very easy to calculate the numbers outside. But then the inverse problem is this one. Still not like super difficult, but it's an inverse problem nevertheless. We need to find some numbers inside that will match the sums outside. And even with this one, the simplest tomography, there is some trouble. Namely, we have non-uniqueness. I can cook up another little grid patient that has exactly the same measurements. But then, well, someone could point out that there's a weird -1, which means that the X-rays are getting stronger in this material, which is not physically possible. But nevertheless, there are more. There's another patient that results in exactly same X-ray images than our original patient. So how can we make a difference between them? We need to pick one when we do an inversion. How can we do that? But before that, let me mention that where these weird non-unique examples come from is the presence of ghosts. Ghosts in a mathematical sense, it's a non-trivial target that produces 0 measurements. So this is invisible in our measurement. So now I can add a ghost to any target, and I don't change the measurements at all. That's how I constructed this example of non-uniqueness. And maybe just to mention, this can be dealt with linear algebra, which is a beautiful part of mathematics. We can build a matrix. So here in the first row of the matrix, we have lengths of paths. So path length inside pixel 1 is 1, pixel 2 is 0, pixel 3, 1, and pixel 4, 0. We can fill in one row in the matrix for each measurement we have, and we fill in the measurement vector on the right-hand side also for each measurement we have. This is our measurement model for limited data case. So not anymore like integrals and projections and stuff. Now we are in the world of linear algebra, and we can observe that this matrix has a non-trivial kernel. So it will map any. Oh, I picked wrong. Sorry. This is bothering my slides. I did this problem once. So plus t minus t minus t plus t. Yeah, sorry about that. So I thought I removed all the incorrect ones. Okay, so with this replacement of this minus sign, we have the kernel of the matrix, and that's where the troubles come from, this non-uniqueness. So how to deal with that? How to choose the right candidate? Let's do a little bit like we did before with the 3 candidates we had in the tomographic mysteries I showed you. For a minute, let's assume that we have 3 candidates, and we should compare them with some criterion, how to pick the best one. This is called regularization in inverse problems. One of the very basic techniques. We are making a weighted sum of 2 penalties. One penalty is if the target is not giving the right measurements, and the other penalty is for being the wrong kind of target. So we think that the tissue type, I wrote there, the tissue type, so let's think that inside a patient, we should have rather large areas of constant attenuation, which is one internal organ, and as few as possible of them. So let's think maybe this is what our expected targets look like. So in that sense, the middle one is really perfect. I mean, it just has one huge area of the same number. So this has good tissue type. Then I picked our non-uniqueness candidate done with the ghost. It has exactly the same data than our original, but it has like three. It has this 0 area, it has this 4 area, and it has this 9 area. So there are too many different areas, and they are too different. So this is bad tissue type. So let's see how these guys compare. So first of all, we measure the data penalty. Well, this is very simple for the first case because this is our original target. So our data penalty is just 0. No penalty because the data is perfect. But then we measure the tissue type penalty. This is the total variation in discretized form. So we take neighboring pixels. Here, the top 2 pixels, we subtract the numbers and take absolute value. Then we take another pair of neighbor pixels and yet another pair of neighbor pixels and the final pair of neighbor pixels. We run over all neighbors in our picture and we take the absolute of the pixel difference. So now when we calculate this one, the penalty becomes 10. So now we can summarize our penalty for the original target. It has penalty of 10 euros, 0 plus 10. Now we go to our flat candidate. So we measure, and the measurement is 6, but the measurement should be 8. So we have 6 minus 8, that's minus 2 squared. That will be 4. We measure here, it gives 6, but it should give 9. It gives 6, but it should give 4. It gives 6, should give 13. So now we calculate this has 66 euros of penalty. So prior penalty is 0. Everything is just the same. So for this guy, we get 66 euros penalty, although all the penalty comes from the data. And finally, we have this guy. This has perfect measurements. So the data penalty is again 0. And now we can calculate these differences. Here's a huge difference. It's 9. And here 4 and 5. So this has 18. Now we are comparing our candidates in terms of 2 penalties. We see that the original one has the smallest, which is kind of good. But then these other candidates, we see that they are worse. They are worse than the original, so we shouldn't maybe pick them. And again, we are in the position having 3 candidates, which is not realistic. We should calculate our image. So how to do that calculation? We do it by optimization. So we write the data penalty. In general form, we give names to our unknown numbers, x1, x2, x3, and x4. We write down our 2 penalties, and then we need a method, an algorithm that will find out the 4 numbers that give the smallest value for this combined penalty. It's a bit tricky because we have a square norm term and we have an L1 norm term. So optimizing something like this is not completely straightforward. Actually, it's been under heavy research for 25 years, and now there are actually really super good methods for it. I will not go into the details of the method, but I'll just show you that when I apply one method for it, this is the solution we get. So we do have 2 internal organs. We have the muscle with 2 1/4, and then we have the bone with 6 1/4. It's not completely equal to the original, but well, how could it be? I mean, we calculated this from the data. So according to this principle of 2 penalties and the other penalty being the tissue type penalty, this is what we get. And there are no other 4 numbers that would give a smaller penalty than 9 euros. That's it. So that's a way to calculate these images, and that's how we do it a lot in the inverse problems community. And now, of course, it's only 2 by 2, but we can choose our computational grid. We can choose it to be more and more accurate. Of course, calculating these line paths inside pixels becomes more complicated. There are more pixels. There are slanted X-rays, not only horizontal and vertical, but it's something that definitely can be done, and there are softwares for that. Well, I've done once or twice by hand an algorithm like that. It's very educational, but I wouldn't recommend doing it very many times. If you get interested in this kind of pixel-based tomography, I'm building up a course also in YouTube. And there's a lot of free sources for software and useful stuff. And data in Finnish Mathematical Society, we published a lot of tomographic data and algorithms. All right. Hey, also there's a little advertisement here. A pretty new journal, our second year going on with Jennifer Mueller. We started a math journal for work that involves real-world measurements. Have work like that, please submit to our journal. Oh, hey, we have some more hydraulic press stuff. There's Lauri are working on it. Oh, what will happen to an Easter egg? Let's see. The structure is round, so it's very, yeah, okay. No match for the hydraulic press either. Yeah. Amazing. Okay, and the final part of my talk is a very mathematical remark in nature, because so far I talked a lot about tomography, but everything was related to X-ray physics and X-ray measurements, but the same math can be used in so many different situations as well. Namely, this is some work by Johanna Tamminen, who works in the next building in the Finnish Meteorological Institute. Some years ago, she worked with this problem where there was this instrument in Envisat satellite. There was this GOMOS instrument looking at the ozone layer of the Earth, measuring starlight attenuation through the atmosphere. It's exterior tomography because we only get the rays that go through the atmosphere. The light wouldn't pass through the Earth itself. So it's also limited data case. I think we might have a little. Yeah, so there's the Envisat satellite going around, and what the satellite did, it will pick some star and measure how the light is attenuating through. So it takes another star and measures. It went around the Earth 400 times a day and collected these kinds of data, actually with some spectral content. Also the color of light was important. And doing like this, it collected very many points around the Earth and could actually monitor. After tomographic reconstruction, we could see a map of ozone thickness all around the Earth. Another visible light application is something that Tapio Helin has worked on, our former postdoc here, now professor at LUT University. With telescopes based on Earth, there's some turbulence in the atmosphere. The image is vibrating in weird ways, where there are some turbulence experts in the room as well. So, but this is the way to counteract turbulence. There are some guide stars, either real stars or laser beams. They monitor how the picture is changing, and 1,000 times a second, they deform the mirror of the telescope to counteract the turbulence. And this involves solving a limited angle tomography problem. The limited angle is only 0.1 degrees. This is the effect. If you look at the Neptunus in Finnish, the Neptune, if you use adaptive optics, you will get a lot clearer picture. And this involves tomography with visible light measurements. Then instead of X-rays or light, you can also use electrons. As we know from quantum physics, electrons are also waves, so we can use them to image very small things, such as coronaviruses. We can even do tomography. In this remarkable paper, they examined in 3D how a cell is producing new coronaviruses after infection. Here we can see the swimming engine of a bacterium, based again on electron microscopy. And let me again say that the math is the same. I mean, the physics is very different, but the math is the same. And then one of my favorites, neutron imaging. Things look very different under neutron radiation. This is just regular X-rays. You see the metal parts are dark because the X-rays are not going through. In this case, plastic is transparent. For neutrons, plastic contains hydrogen, which is scattering the neutrons away. So we don't see through plastic, but metal is almost transparent for neutrons. So we get this kind of compensating way of imaging. And we can, for example, see how coffee is made. I'm sure, I mean, well, at least I had been wondering for a long time what is actually happening inside the aluminum coffee pot. So Anders Kestner was kind enough to share this video they shot in Switzerland in Paul Scherrer Institute. Here we can see through the metal because it's transparent almost to neutrons, but water with hydrogen and plastic parts with hydrogen are very attenuating. So we can see what happens inside. Tomography-wise, researchers can look at big pieces of rock that has fossils inside. These are old cones of extinct trees. So instead of hacking them out with a hammer and maybe breaking the cone, researchers can take neutron images from different angles, use the same mathematics and recover what's inside. And recently, they also used this technique to look at a fossil crocodile, Confractosuchus sauroctonos. And once they had the 3D reconstruction, they could identify this species and look at the bone shapes and all. And then they also noticed that there were some parts not belonging to this animal. The red ones are stomach contents. So there was the last meal of this crocodile, and they could also identify that one. And well, this is not tomography anymore. This is more an artistic illustration, but this is what must have happened a long time ago and then preserved to us in stone and revealed to us by neutrons and mathematics. Thank you so much.